series RLC circuit, or simply you can keep the main heading as RLC circuit excited by sinusoidal source under that series RLC circuit. Okay, series RLC circuit, and you have to connect your resistor, inductor, capacitor in series combination across the voltmeter, where there is a flow of current I of t which is passing through series connection of your resistor, inductor and capacitor, right? So all of you draw the circuit. Once the circuit is drawn, go for phasor representation. So will you draw the phasor representation by your own? For individual resistor, inductor and capacitor, will you draw that? For resistor, how V, R and I?
In
V,
phase.
R and I in phase, right? And for inductor, here what
Out
is
of
the
phase and we lead by 90 degrees.
right? That is VL leads I by 90 degrees. And what about capacitor? VC with respect to I,
IC lags I by 90 degrees.
right? VC lags I by 90 degrees. Here, why I am considering I as a reference? Since
In series,
RLC, right?
instant.
Since the
RLC
circuit is in series.
in series, right? Because R, L and C, three components are connected in series combination, where in series we know that the current is remains the same, which is passing through each component which is connected, right? So therefore, once you see that the reference parameter as I, if you consider the resistor, VR is in phase with respect to I. And what about VL leads? VL leads in the sense, in which direction I need to draw? VL,
Upward direction sense.
right? It should be your VL, right? And what about VC? From this origin point, lags I by 90, right?
Downwards.
Minus j omega x is simply, right? So is it clear to everyone how I can draw this phasor representation for series RLC circuit? Now further refinement, I can shift this negative phasor to the positive phasor. So shall I redraw the same phasor representation for our convenience, like VL minus VC, right? By shifting the VC into the positive j omega axis side, shall I keep the negative sign?
Yes, sir.
Right? Therefore, what is the resultant now? It should be easy to draw the resultant vector now, right? That is VR plus VL minus VC. That is our total voltage. This one, VS. Total voltage, VS, which is applied across the circuit. Right? We can see that. See this here individually. I explained what is the first statement that will indicates that your resistance, ohmic resistor, that should be reflecting this waveform, that is both voltage and current. VR, see here, VR, that is in phase with respect to your current, right? And what about second sentence? In a pure inductance, that is this one, in a pure inductance, the voltage waveform leads the current by 90 degrees. So therefore, VL will be starts at the positive j omega axis. This is for sinusoidal representation. Later we can go for your regular phasor vector representation. Right, by 90 degrees. See, this is your regular phasor representation, VL, which will leads with respect to I. And in pure capacitance, see, pure in the sense it should be 90. If they are not mentioned pure, then that will be some angle phi. Okay, not 90, that should be some angle phi if it is not a pure one. So here in the pure capacitance, always the voltage will be going to lags the current by 90. Lags in the sense where it is going to start at the negative j omega axis. Right, clear? Understand the sinusoidal representation? and later we will move on to individual voltage phasors. As per our phasor diagram representation, for resistance I and V are in phase, and for inductance VL leads current by 90 degrees, and for capacitance VC lags I by 90 degrees. So up to this, anyone having any doubts for series RLC circuit? Now just we are going to club all three into one phasor representation, what we drawn in first slide, right? Both are same, any different? Clear? Everyone have the clarity? All of them are confident to draw the phasor diagrams, whether any combination they given in exam, either RL, RC, RLC, right? Parallel series
Yes, sir.
circuit, right? Okay. So here coming to our mathematical expressions, what is Vs? Vs is nothing but Vs is equal to Vr plus Vl minus Vc, right? At an angle 90, where that should be represented by J later. So where if you wanted to go with the magnitude value, then it should be under root of Vr square plus Vl minus Vc whole square. But if you go for individual, what is Vr? What is VL? What is VC? Where here I mentioned VR is nothing but I into R, VL IXL, VC I into XC. Same what we did for RL RC circuits, just we are clubbed all three components into one circuit. So therefore Vs is equal to, substitute your VR, VL, VC values in this equation. So by substituting, Vs is equal to under root IR whole square plus I into VL is nothing but I into XL, and minus Vc is nothing but I into Xc whole square. So therefore, by taking I as a common factor outside of the root, because I square, so Vs is equal to I into under root of R square plus XL minus Xc whole square, where entire this one should be your impedance, that is Z, for series RLC circuit. So for series RLC circuit, the impedance value, if anyone asking you for series RLC circuit, the impedance of the given circuit, total impedance of the given circuit is under root of R square plus XL minus Xc whole square, where XL is nothing but inductive reactance. What is the formula to calculate XL?
Omega L.
Very good. Similarly, Xc, the capacitive reactance, what is the formula?
1 by
1
omega
by
C.
omega c.
Very good. Right. So therefore, shall we able to calculate the impedance value, total impedance value of the given circuit, by knowing
Yes,
this
sir.
XL, XC and R value also? So that once we know the value of Z, shall we calculate I value, current passing through that, by doing Vs by Z, right? So by this we can solve the numericals which are asked under series RLC circuit concept. Okay. Next, just for your reference, already we seen this, but note it down for your reference in the examination point of view, the definition of impedance of a series RLC circuit. The amplitude of the source voltage is proportional to amplitude of current flowing through the circuit. What does it mean by exactly? Voltage proportional to current. If you remove that proportionality constant, proportionality, we should kept one constant, that is your impedance Z, like your capital R, where Z is the combination of your real term and imaginary term, R and X, where R is the resistance and X is the reactance term. That should be going to vary based on the circuit to circuit. The imaginary value should be going to vary based on circuit connection. Your resistance value should be remains same, right? If you take RL series, it will be different. RL parallel different. RC series different. RC parallel different. RLC series different. Right? The value of Z should be going to vary according to the circuit connections and the components which are presented in the circuit. Clear? For this RLC circuit, what is the impedance formula? Z is equal to under root R square plus XL minus Xc whole square. Here I am resubstituted XL value as omega L. Therefore, Z equal to under root R square plus omega L minus Xc, in the place Xc I replaced with 1 by omega C. So therefore, for that I drawn the right angle triangle by indicating real axis as capital R, the real term, and imaginary axis as imaginary term of reactance. Therefore, the hypotenuse will become your impedance. The units are ohms. Quickly note down all of you the definition of impedance and the value of impedance for series RLC circuit. Hema, you can leave, ma. Hema. Hope you have some another session. You can
So
leave.
after 5 minutes,
Yeah, sure. Okay, fine.
I'll join after that.
Okay.
Thank you, sir.
So quickly, series RLC circuit done. So shall we go for parallel RLC circuit? Before that, there is one numerical. We can solve it later once we will finish the parallel RLC circuit quickly. So all of you draw that parallel RLC circuit where R, L and C, all three components are connected in parallel combination across your voltmeter. So where Vs is the voltage which is applied to the total circuit, that is the total voltage Vs, and current passing through that, the total current is Is, that should be going to dividing as IR, IL and IC, because this is a parallel combination. You can also draw the circuit like this. In some of the textbooks, they may mention like this: R, L, and C. Both are correct. Okay, don't confuse. This is your Vs, current passing through Is. This is a junction point where it should be going to dividing to the remaining branches as IR, IL, IC. Understand? Both remains the same. Now tell me immediately what about the phasor representation for parallel RLC circuit for resistor? What is the reference parameter we need to consider?
Current.
Current. Clear? The reference parameter should be?
See, what
Right, very good. Reference parameter is voltage, not current. Good. So why it is voltage? Because voltage is constant for parallel connection, right? So then take individual parameters of resistor. What about resistor, the components IR and V? How they are? How these two are getting
inputs.
in phase? Right. That means IR, right? And what about IL for inductor? IL with respect to V? Always current in inductor with respect to voltage.
I lakhs V by
Right.
90.
Right. I lakhs V by 90. Similarly, what about for capacitor? I lakhs in the sense I need to draw downward. And what about capacitor?
I leads V by 90.
Right. I leads V by 90. Leads in the sense I see. Done. We will verify whether this one is correct or not. We will move on to next slide. Right. Check here. For resistor, done in phase with respect to your V, and IL, current lags voltage by 90, and IC, current leads the voltage by 90. Done. Now just I am keeping the positive j omega axis to negative, so that's why I changed the sign of your IC value, IL minus IC, and therefore where I drawn the net resultant vector, that is total current IS. So where IS is nothing but simply IS bar equal to IL minus IC bar. Clear all of? I think here you may
Yes,
get
sir.
one doubt that, sir, why you are shifting the positive to negative? Why can't we shift the negative to positive? That means IC minus IL. Both are correct. No need to worry. But in order to make the similarity in the sense what we did for series RLC, the expression should be like, one second, check here, the expression should be like VR square plus VL minus VC, right? So same in the same replica here I mentioned as IS equal to IR plus IL minus IC. So in order to form the same fashion, I changed the pattern. Understand now? For your easy convenience, if it is series, Vs equal to VR, VL, VC. In the place of I, just V. right? If it is a parallel, it should be current. Understand now? The sequence will be remains the same. Or else if you take, if you are shifting IL to the positive j omega axis, that will become how it should be IC minus IL whole square, correct? So whether it should be IL minus IC or IC minus IL, whole square value remains the same or not? Understand my point? Manoj, Devi Priya, are you able to follow?
Yes, sir.
Right, right.
Yes, sir.
Right. So in order to make that similarity, I changed this positive j omega axis will be shifted to your negative. So therefore, the pattern will be same as your series circuit, like VL minus VC. Now it should be IL minus IC. So therefore, where I calculated the resultant, the total current IS value, right, the magnitude value, and therefore by substituting the individual values, where IR is simply V by R. Right, here it is. IR equal to V by R, and IL is V by XL, and IC is V by X. Same we are substituted, and that equal to similar to V by Z. So shall I write this V by Z as V into Y, because reciprocal of Z is simply admittance, right? Reciprocal of impedance is called admittance Y, right? Already we seen in RL parallel circuit and RC parallel circuit. Right. So this is your impedance of the parallel RLC circuit, useful for your numericals, the formulas, where 1 by Z is nothing but capital Y. All these are came from your mathematical expressions, what we drawn for phasor representation for the given parallel RLC circuit. And then note down the admittance and its definition for your examination point of view. For a parallel RLC circuit produces the complex impedances for each parallel branch as element becomes reciprocal of impedance. That will be very important. The reciprocal of impedance. That will be called as your admittance, given by the symbol Y. See, in this point, the admittance of a parallel circuit is a ratio of phasor current to phasor voltage. What we obtained here, Is equal to V by Z, right? Is equal to V by Z. Here I will draw that. Is equal to V by Z. That is V into Y. Then what is Y? Is by V. See this definition, the admittance of a parallel circuit is the ratio of phasor current, right? This is your phasor current to phasor voltage, to the angle of the admittance being the negative to the of impedance. Understand? The third point, the
Sir, you are
ratio.
not on.
My voice is clear to everyone?
Yes, sir.
Okay, yeah, fine. So all of you understand the admittance concept, impedance concept, and series and parallel RLC circuits, the phasor representations and mathematical expressions. Clear everyone? Avinash, Srinivas,
Sir, yes, sir, it's
and
clear.
understand? Okay, fine, fine.
Yes, sir.
Right. And note down conductance, the definitions which are useful for your short answer questions in examination. Conductance represented by capital G, that is a reciprocal of your resistance. These all are we discussed in morning, but anyhow, for examination point of view, note down the definitions, where G is 1 by R, and the susceptance, reciprocal of reactance, that is B equal to 1 by X. If it is for L, then we can represent that as suffix L, that is B suffix L and X suffix L. conductance, which is the reciprocal of resistance, and susceptance, which is the reciprocal of reactance, that is represented by capital X reactance, and susceptance represented by capital B. And what we drawn for active power, reactive power, and apparent power, the power triangle, same already we drawn, right, for impedances and admittances. Same you need to draw neatly, the admittance triangle and impedance triangle. This is your impedance triangle, that is real term R and imaginary term X. Therefore, the hypotenuse is your Z. Similarly, the admittance triangle, the reciprocal of resistance, that is the conductance 1 by R, and the susceptance capital B, and the hypotenuse will become your admittance. Very important, power triangle and impedance triangle and admittance triangle, the formulas for your numerical problems. Noted. Admittance triangle and the formula for admittance in parallel RLC circuit, and impedance the same what we obtained in the phasor representation, the same here mentioned as a separately, because that will be useful for the problems. So all of you note down all the formulas in unit 2 in a separate pages only for formulas.
Sir, once you can show that before slide triangles.
Yeah.
Sir.
Done. Okay, fine. Parallel RLC circuit admittance. Nothing but simply 1 by R whole square plus 1 by XL minus XC. XC is nothing but 1 by omega C. Therefore, 1 over 1 by omega C, that should be again reflected as omega C. That is your admittance part. So once it should be getting finished, we will go for the numerical problem. Done, all of you? Shall we go for problem? We will do one problem in today's class. Done, ma, all of you? Shall we move on to problems?
Yes, sir.
I hope all of you done, right? So note down the problem. Right. Note down the problem. A series RLC circuit containing a resistance of 12 ohms and inductance of 0.15 henries and a capacitor of 100 microfarads are connected in series across a 100 volts 50 hertz supply, which is shown in the figure also. 100 volts 50 hertz supply across a series connection of your resistance, inductance, and capacitance. Their values are also given. Then we need to calculate the total circuit impedance, circuit current, and power factor. So will anyone tell me the formula for total circuit impedance for series RLC circuit? What they given? R value given, L value given, C value given. So what is the total impedance formula? Z equals to under root R square plus XL minus
Excel.
XL whole square, right? So how can we calculate XL? XL is equal to omega L.
Omega into L.
What is omega? 2 pi f into L.
2 pi f.
So they given f value also in the given problem as 50 hedges. So will you substitute and calculate XL value by your own? And similarly XC value, that is 1 by omega C, 1 by 2 pi f. See, all of you concentrate on the screen. Later you can do by your own. Xc is equal to 1 by 2 pi fc, right? Where f value you know, c value you know. So will you calculate xc value by your own? And by substituting here R, XL and XC values, will you able to calculate the total impedance Z? Understand the procedure, how to calculate the
Yes,
total
sir.
circuit impedance? Right, this factor is done, total circuit impedance. Once impedance should be getting calculated, what is the formula of current I equal to V by Z, right? So V value they given as 100 volts in the given data. So 100 minus whatever the value you obtained, substitute. So will you obtain the current now? Total circuit current. Clear how to calculate the circuit current now? Then what about power factor? See here, once check your impedance triangle, phi R XL minus XC Z, right? This is your impedance triangle, correct or not? The impedance triangle.
Yes, sir.
So from this, what is cos power factor in the sense cos phi, right? So what is cos phi from this triangle?
R by
Hmm.
XL minus.
Cos theta.
R by Z.
Very good. Adjacent side by hypotenuse. So already R value given data and Z value you are calculated. So will you substitute and find out cos phi? That is your power factor. Done? Will you do by your own? Still having any queries to solve this problem? So all of you will do by your own. Entire procedure is in front of you.
Yes, sir.
Right, good, very good. All right, thank you, ma. Thank you all.